Can you start it
Shown
off?
here is the beautiful hand. It will help us. It will help us fill out the unit circle. Check this out. Okay, so this is 0, this is 90, this of course is 30, 45, and 60. Okay, so let's say that you want to find the cosine and sine of 30. You would then bend this finger down. Okay, so bend this finger down. Okay, I will try to draw a bent version of a ring finger. There. I bent it in. Yeah, it's a little broken. So, how many fingers, including the thumb, do we have on the left side of the finger you pulled back? 3, right. That means cosine is square root of 3 over 2. Okay? Cosine is
what?
square root of 3 over 2. How many fingers are to the right of the finger you pulled back? 1. So this would be square root of 1 over 2. Okay?
Oh, that's like too much work. You think the AP test like.
Yeah, you can do this during the AP test. Okay, let's try the middle finger. Okay, so the middle finger, if you bend that down. Okay? I know, I broke it. This is square root of something over 2 and square root of something over 2. How many fingers to the left? 2. How many fingers to the right? 2. This works on every finger, including the pinky and the thumb, believe it or not. Okay, so let's put this finger back. Okay, let's do 60 degrees. So we bend this finger. Right? I know, that's weird. It's square root of something over 2, square root of something over 2. How many fingers on the left? 1. How many fingers on the right? 3. Okay? Obviously, this is just the point 1, 0. This is the point 0, 1. You can actually verify that by pulling that finger down. There are 4 fingers on the left of 0 degrees. Right? And none on the right. So square root of 4 over 2, aka 1. Square root of 0 over 2, aka 0. So it actually works with the quadrantals as well. So a great little trick someone taught me, and I'm sure you can use that if you need to get quadrant 1. Obviously, if you have quadrant 1, the rest of the quadrants kind of come together just by reflecting. So this is just root 3 over 2, 1 half. Square root of 2 over 2, square root of 2 over 2. Square root of, 1 half, square root of 3 over 2. And this is 0, 1. Then just change your x's to hop over to the left. Change x's and y's to hop to the 3rd quadrant. And change your x's again to go back to the 4th quadrant. Okay. Remember, pi means 180, which means this is pi over 6. Think of it as 180 over 6. This is 45 degrees, of course. So that would be pi over 4. It's 1/4 of 180. And this 60 degrees represents 1/3 of 180, or you could say pi over 3. This, of course, is pi over 2, also known as 90. Okay? All right. So let's go ahead and look down further in our packet here. I didn't know how much polar stuff you guys remember. So I think what I'm going to do is I'm going to go over the basics, and I'll go over some problems where we convert the functions. Where we graph the functions. As for pages 4 and 5 of this packet, I'm going to skip those pages and make a separate video for those during 6th period today. And I'll post that for those who need it, but I don't know that everyone needs it, so I'm not going to waste too much class time with it. Okay? So does everyone understand? I'm going to basically do this page here, basics, and I'll do most of this page. This page I'm skipping. This page I'm skipping, and then we'll jump into the calculus. Okay? If you need the 2 converting pages, you'll have to watch a separate video for that. Okay, so basics. A point on a Cartesian grid, x, y, can be labeled with its x and y coordinates, which of course just means you travel to the right by x and up by y. So the legs of this triangle represent basically the coordinates of this point. This is a very, very convenient system. Okay? A classic example might be, you live here, this is home, and then this point over here, I don't know, maybe is Jamba Juice or something. And you live, let's say, 3 blocks to the west of Jamba Juice. So you could say Jamba Juice is 3 blocks east of you, and 4 blocks north from your house. So this would just be the point 3, 4, right? Well, somebody else might not travel the same way you do to go to Jamba Juice. So maybe you travel 3 to the 4 and 4 up, 3 to the right, 4 up. But maybe they have a helicopter or something. So they like to fly to Jamba Juice. So as the crow flies, this distance is actually 5. And if they're going to fly, they need an angle to fly along. So every pilot knows they need a directional angle. So this angle would be 53 degrees. It's actually 53.130. I use this example a lot. So which is the correct coordinate representation for Jamba Juice? Is it 3, 4, or is it 5, 53.130? They're exactly the same point in space. Okay? The first one is called the rectangular coordinates, or Cartesian coordinates. The second one is called the polar coordinates. Okay? Both of them describe perfectly the location of Jamba Juice relative to the origin. Okay, the problem with the red, the polar version, is that there is more than one correct way to write that point. Okay? So let me go back to here real quick. So what I'm saying is the point 553.130 has other names. Okay? For example, you could label it as 5, 413.130. Now why is that the exact same location?
It's been around once before.
Yeah, there's like an extra 360 added on here, but that doesn't matter because going 360 degrees around the origin brings us back to the same location anyway. So that's interesting that even though there's only one Cartesian representation of this point, 3, 4, there are 2 polar representations. And that's not all, there are more. For example, you could say 5, negative 306.870. Why is 5, negative 306.870 also the same location for Jamba Juice? It's just a reverse direction angle, right? But it's the same exact point in space. So how many ways are there actually to represent
Infinity.
a point in polar coordinates? An infinite number of ways. Okay, here's a kind of a weird way to do it. I could actually call this point negative 5, watch this one, this one's kind of weird, 233.130. Now you might say, that's going too far, Mr. Shore. 233 is over here.
Yeah, but it's
Well, in polar we often will draw concentric rings, kind of like a target, concentric rings to show how far a point is away from the origin. Okay? So here is a drawing, and I'm trying to convince you that the point negative 5, 233 is the same thing as Jamba Juice up here. Well, it is because if you told somebody to travel in the 233 degree direction, they would most likely follow this purple arrow. But if you told them to travel negative 5 units along the purple arrow, they would be forced to walk backwards, and they would end up here at Jamba Juice. So an angle can have a 360 added to it, and it doesn't affect your spatial position. Okay? We call that trivial rotational symmetry. And you can go backwards to that angle, or, look, you can even say negative 5, which is technically on the other side of the circle, as long as you give me the angle that's on the opposite side of the circle. So all of these 4 are the exact same location. Okay, so that was a pre-calc idea that you hadn't seen in a while. I thought I'd just kind of bring that up again. But I kind of listed that here too. I said we can describe the same point using polar coordinates. There are an infinite number of representations for any point. When we graph in polar coordinates, we don't call the origin anymore. We actually call it the pole. Okay, that's kind of weird, but this origin point is actually called the pole, not the origin origin anymore. And this is no longer called the x-axis, it's called the polar axis. But that's just semantics, okay? Those are just names. And you don't really have to know that. We even have polar graph paper, which I have some examples of down here. These are polar graph papers down here. Okay? In pre-calc you learned several polar patterns, but I wouldn't expect you to remember many of them or any of them. So what I want to do is just show you how you can still sketch a polar function even if you cannot remember at all anything from pre-calc. Okay? So let's take a look at this first one. I always tell my pre-calc students, if you're given a new graph and you don't know what it looks like, just make a table. Now if I've already taught a graph, they're not allowed to make tables. I don't let them do that. I make them memorize their graphs. Okay? So, but this is a new one, and maybe you've never graphed it before. So let's go ahead and put in some friendly angles. I'm going to say some extremely important things. So if you've already tuned me out for the day, you really should think, I'm serious, you really should think about listening. Okay, I'm also about to get out my calculator, so I have some very important things to say. This can be calculated by hand. You're going to plug in the thetas to produce the r's. So if you plug in 0 radians, you get 3 cos 0, which is just 3 times 1. Then you're going to do 3 times cos pi over 6, which is 3 times a half. Then you're going to do 3 times cos pi over 4, which is, basically this comes out to 2.1. And here's how I know. Rad 2 is about 1.4. I'm making my pre-calc students memorize that. Oh, question?
Isn't cosine pi over 6 rad 3 over 2?
Oops. This is supposed to be the rad 3 over 2 case. Thank you.
Wow, you had that whole hand thing and everything.
I did. I'm also a little short on time here, so I'm rushing. Sorry about that. I make my students memorize that rad 2 is 1.4 and rad 3 is 1.7. That's very important. Okay? So this is approximately 2.5, and this is approximately 2.1. Root 3 over 2 is about 0.85, and root 2 over 2 is about 0.7. You shouldn't be using a calculator for this kind of stuff. Okay, pi over 3 is the 1/2 case. Thank you. So this is 3 times a half. This is 1.5. And then 3 times cosine pi over 2, that's just 0. Now I might need more points, but here's what I plan on plotting. I'm plotting the points 3, 0, 2.5 comma pi over 6, 2.1 comma pi over 4, and 1.5 comma pi over 3, and lastly 0 comma pi over 2. You'll notice that when we actually write the ordered pairs, this is kind of weird, but history kind of unfolded this way. We list the r first and then the theta. Isn't that strange?
That makes sense.
Even though our table contains theta, an independent variable, we list it last. So that's kind of strange. Normally in x and y, you list independent variable first. Okay, so that's kind of backwards. But anyway, what it really means is we will be on the third circle when the angle is 0. We'll be between the third and second circles when angles pi over 6 and so on. You can also see that this grid is laid out where this is 0 degrees, this is 90 degrees. So the 30, the 45, and the 60 are all right here. And you're going to be ignoring, basically, the first and last ray in each quadrant. Because that stands for 15 and that stands for 75, and those just aren't special angles. Okay, yeah, it's kind of sad. They're not special angles. Okay, so let's plot these. So far we only have the first quadrant. 0, 3 means third ring. I'll use blue. Third ring at 0 degrees. And then when we go to the pi over 6 ray, we're at the 2.5 ring. So it looks something like that. And then when we get to pi over 4, we're on the 2.1 ring. And when we're at pi over 3, we're on the 1.5 ring. When we finally reach 90 degrees, we've recycled back to the pole. Okay? So in order, what we did was we went up and down and hit the pole. it looks like it might be a semicircle. Now, if I were to keep my table going, what would happen next is kind of unpredictable. Okay? But cosine of pi over 6, right, is the same as cosine of 5 pi over 6. No, cosine of pi over 6 is cosine of 7 pi over 6. Correct. No, 11 pi over 6. So there's some symmetry. You can kind of figure out other points based on that. But if you keep making this table, you'll be able to see the full mapping. I'm going to argue that this is a circle, and then I'm going to show you how you can prove that without plotting a bunch more points. I believe this thing's going to close in on itself, and I believe it's going to close in on itself when we reach pi. I think the entire circle is going to be done mapping when I hit pi. Okay? Now, how do I know it's a circle? Well, partly from experience. But also, if you look closely at this equation, look closely. R equals 3 cos theta. When you plot a point at x, y, and this is r and this is theta, okay? The relationship between x and y and r and theta is x is always r cosine theta, and y is always r sine theta. That is a very important formula. You might even want to put that at the top of your packet, okay? X is r cosine theta, y is r sine theta. That's always true. So I'll highlight it at the top here. Very important. So looking at this equation that we were given, down here in yellow, if you multiply both sides by r, you get this. R squared equals 3r cosine theta, right? And r squared is simply x squared plus y squared. It's just the hypotenuse of the triangle squared. And this is just simply 3x. 3x. So now I'm 100% convinced that this is a circle. Look at this equation. That's the equation of a circle. In fact, I can go so far as to move the 3x to the left side and complete the square. So I could write it like this if I wanted. It's minus 3x. And you can complete the square by adding a 9/4 here and here. And sure enough, this is a circle. X minus 3 halves squared plus y squared equals 9/4. This is a circle with center at 3/2, 0. And radius square root of 9/4, 3/2. Exactly like I drew up here in blue. Center is right at 1.5, radius is 1.5. Okay? So you make the table to kind of get an idea, or if you're comfortable with what I just did, you can try this on your own. You can actually show what the equation is in Cartesian coordinates, and you can say, oh, that's a circle. I don't need a table to graph that. Okay? Now it's time to get out the calculator. I want to show you something very important. I claimed, and I didn't have any reason to claim it, really. I just kind of said I believed that the entire circle could be sketched just between 0 and pi. Okay? So what I want to do is go under mode and turn this calculator on to the polar mode. I want to show you why I believe that. Okay? Put this on polar mode and make sure it's in radians. You might have it in degrees since you've been working with vectors recently. Okay? So radians and polar. And when you press this, it now says R1, R2, R3, and so forth. We're going to go and graph 3 cos theta. Your old button for X is now a theta button. Okay? Now if you press graph, you see what looks like a circle. It looks kind of like an oval, and the problem is the scaling. So this piece of plastic they used when they made the calculator wasn't a square piece of plastic, this little screen. So you need to do a zoom square, and that will make it look more square. It's option 5 under zoom. Yeah, that looks like a circle. Let's zoom in on it once. Boy, that looks like a circle. In fact, we already proved it was a circle, right? What you couldn't see is that the calculator just drew this circle twice. Okay, you can't see that, but watch how I know that. If you press window, the calculator says 0 to 2 pi there. See that for theta min and theta max? If we change this to just simply pi, watch what happens. Graph. It drew the whole circle. So some people really struggle with this. They're like, I don't understand how the calculator is able to draw an entire circle if it's only going around to 180. How can it do that? And the reason is because cosine takes care of all of its important business between 0 and pi. All the possible lengths of r are defined when theta runs from 0 to pi. Everything from positive 1 to 0 has been mapped out. So we get this full circle effect. Okay? So this is very, very important. On the board over here I have some formulas that we're going to use in a minute for calculus. Okay? The first one is position. X is r cosine, y is r sine. You already wrote that at the top of your page. Okay? The second one looks a lot like parametric. Look. Remember parametric was y dx is dy dθ over dx dt? Well, here, dy dx is dy dθ over dx dθ. And it gets a little complicated after that. But this area one is very challenging because to find the area of these little sectors, which are our differential areas in polar world, we have to use this integral. And the problem with it is the a and the b are a little bit hard to figure out. For example, if I wanted to find the area of this circle using integration, my first thought, listen, my first thought would be I'm going to integrate and I'm going to let my least angle be 0 and my largest angle be 2 pi. That's just the common sense thing you think, you know? Well, it turns out if you try to find the area of this circle using integration, which we'll do tomorrow, you would be tempted to do 0 to 2 pi, but you will get twice too much area. Because this circle doesn't need 0 to 2 pi to be mapped out. It only needs 0 to pi, and we get the full circle. In other words, if you're going to solve this area by integration, you need to use 0 and pi here, not 0 and 2 pi. And this always throws people off. Okay? What would happen if I went in here and I just changed this to a 2 theta? And let's make our window go from 0 to 2 pi again. That's sort of the default. By the way, if you ever do a zoom standard, it goes back automatically to 2 pi and you have to come back and fix it. I put 2 theta. Thank you. 2 pi is right here. Okay, so now we've got a brand new graph. It's kind of pretty. This is called a rose. Great name for it. Okay, and it has 4 petals. Who knew? How did I create this thing? I just put in a 2 theta instead of a theta. Now it's 3 cos 2 theta. All of a sudden I get this 4-petaled rose. Do you think maybe it got traced twice? Well, let's go back and look at the window. Watch closely. I'm going to change this to pi. I'll bet I get that full rose again. I don't. What's going on? On that circle I had a minute ago, 0 to pi was enough for this to finish. But on the rose, 0 to pi only gives me half a rose. So if I want to find the area of this rose, I can't integrate from 0 to pi. I have to integrate from 0 to 2 pi to get the full rose. But for the circle that I had a minute ago, integrating from 0 to 2 pi is too much. I can only integrate from 0 to pi. Because from 0 to pi is enough to draw the circle. So this is where people get really confused. Alright? How do I know my limits of integration? Fortunately, we have one more day, and that's tomorrow. We'll talk about that more. But I need to show you that that circle completed itself between 0 and pi, but the rose won't. Alright? That's why you need your graphing calculator handy, so you can play around with it. 0 to pi gives me half a rose. That means 0 to 2 pi gives me a full rose. Okay, this second one's a lot easier. R equals 4. R equals 4. What does it mean?
It's a circle with radius 4.
It does mean that. So, that's obvious, but let me show you how the absence of theta is actually screaming a truth to us. Okay? Some of you are in physics class. So you've seen this equation before. The period of a pendulum is, I think it's 1 over 2 pi squared of L over G. Does that look right? Okay, so there is something missing from this formula that I would have expected to find. I would have expected to find mass in this formula, M, right? You put a heavy lead ball at the end of a pendulum, or you put a feather at the end of the pendulum. How can that not matter? I mean, wouldn't the lead ball maybe swing faster or something? No, it doesn't. According to this formula, since M is absent, I learned something. I learned that it doesn't matter what the mass is. The period only depends on the length of the pendulum and gravitational constant, 9.8. So basically, the absence of M here is telling me something. It's teaching me something new, that periods of pendulums do not depend on the mass of the bomb. Interesting. The same thing is true here. Which variable is absent? Theta is missing. Where is it? Well, what it means is it doesn't matter what theta is. Theta can be anything, just like the mass of the bomb, you see. So if theta can be anything, then R is 4 no matter what theta is. So that creates an infinite number of points. The absence of theta means theta is whatever you like. Now, if you want to, you can convert this one to back to Cartesian as well. Just square both sides. And you get r squared equals 16. And then you can change this to x squared plus y squared. Yeah, it's a circle. Radius 4, centered at the origin. I wonder what would happen if I told the calculator to draw r equals 4. Just simply r equals 4. Let's see. Notice that my window right now is set for 0 to pi. You think I'll get a full circle or half a circle?
Half a circle.
0 to pi.
Half.
Got to zoom out a little. Half. So it looks like we're going to have to go 0 to 2 pi to get the full circle. That's not always obvious, right? A minute ago we saw a circle that was created just from 0 to pi. But that was a different kind of polar equation. That was this equation of a circle. When it's centered at the origin, evidently you have to go 0 to 2 pi to get all the way around. All right. So I was going to leave it to you guys to go through and fill in some of these others. I do want to do this next one and this one next to it. So C and D real quick. This next one is missing a variable. Where is R? It's not present. What does that tell us? This is very important after the AP test when I teach you multivariable calculus. The absence of R tells us what? R can be what? Anything. Right. So theta is negative pi over 4. That's just negative 45 degrees. Theta is negative pi over 4. No matter what R is. R can be 0. R can even be negative. So what is this thing? It's a line. That's right. Passing through the origin. The next one, maybe we could do a quick table for. We make up our thetas, we calculate our r's. If I let theta be 0, then r will be 0. If I let theta be pi over 6, then r will be pi over 6. If I let theta be pi over 4, then r is pi over 4. If I let theta be pi, then r is pi. And I'm used to working with angles in pi's, but I'm not used to working with distances in pi's. Let's make these all decimals. This is about 0.5. This is about 0.75. This is about 3.1. In other words, as we go around from 0 to pi over 6 to pi over 4 to pi over 3 to pi over 2 and all the way to pi, etc., basically what happens is this thing grows. It starts at a radius of 0. When we reach pi over 6, we're out at the half space. When we get to pi over 4, we're at the 0.75 space. When we get to pi, we're eventually out at the 3.1 space. So it's like this spiral look. And if you go all the way to 3 pi over 2, that's straight down, you will spill just outside my graph paper. It's going to end up just outside the 4th grade. This one has a name. Most of them do not. This one has a name. This is called a spiral of Archimedes. Okay? If you're interested in the names, the last 2 sheets of this packet have all the names. But that's probably the least important thing of all, to know the names. Okay? The reason I want to show you these is so you can see how it maps out, like how to plot. That's very important. Now let's try some calculus. I only have time to teach you how to find a slope. That's all I have time for today. Tomorrow we'll do areas. So I told you we'd skip this page and this page. At the top of this page that says calculus with polar curves, I'd like you to write the following. X is r cosine theta. Y is r sine theta. Okay? These are actually 2 things that every pre-calc student knows. Okay, maybe you knew them too. Algebra 2 maybe, yeah. Mr. Gurr just taught that? Good for him. Okay, so if dy dx is dy d theta over dx d theta, right? And y is r sine theta, then this y can be replaced with r sine theta. In other words, f of theta sine theta. See, r is a function of theta. So what you're looking at right here is y, and this is x. Y is, we said, r sine theta. X is r cos theta. The r happens to be a function of theta. Most people just memorize this little rule here. This is how we find dy dx in the polar world. Let's try a problem. Okay? First, let's try to understand the problem real quick. We're on example 5. Here's what's going on. This is a spiral of Archimedes. Okay? It's a little bit tighter of a pitch, like the spiral's not quite as big. It actually goes like this. And it only makes it out to radius pi once the angle hits 2 pi. So it just barely makes it past the 3rd radian when you go all the way around. If the angle's 2 pi, the radius is 3.14. That's kind of what it looks like. And what we're trying to find is the slope at this particular point. We want the slope at this particular point. That is a very simple question. We've been doing this all year long. But the functions have always been given in terms of x and y, right? I want that slope. What do you think it is? -1? Maybe. Let's see. So let's go ahead and find dy dx. You're going to be doing d theta of f of theta sine theta. So this is going to be the function they gave us. Over d theta f of theta cos theta. And then we'll plug in pi over 3. Okay, you can cancel the halves if you want, but don't cancel the thetas. Definitely don't cancel the thetas. You need the product rule. So don't be intimidated by this. This is kind of like finding d dx of x sine x, okay? There's no chain rule needed here. If you can find the derivative of x sine x, you can find the derivative of theta sine theta. It's the same thing. So first you take the derivative of theta, that's 1. And then you leave the sine theta as is. Plus, then you take the theta as is, and you multiply by the derivative of the sine theta. So you basically get 1 times sine theta plus theta times cos theta. And the bottom is very, very similar. It's 1 times cos theta. And then there's a theta times negative sine theta. A little hard to read there, sorry. This is a cosine. The bottom is basically cosine minus theta times sine theta. Okay, now your plan is to plug in pi over 3, which I did earlier. And this gave me, this is right now you're going to circle really well. This is root 3 over 2. This is pi over 3. This is a half. So it's root 3 over 2 plus pi over 3 times a half. So basically it's root 3 over 2 plus pi over 6. That's the numerator. On the bottom, it's 1/2 minus pi over 3 times root 3 over 2. I meant to put, pi over 3 times root 3 over 2. So basically it's 3 pi root 3 over 6. That's not right. Just pi root 3 over 6. Can someone verify that? Getting tired here. Been a long day.
Pi over 6, right? Yeah.
Pi over 3 and then times root 3 over 2. This is correct, yeah. Multiply top and bottom of this thing by 6. To sort of clean it up, I'll put my answer way over here on the left, okay? So my answer for the numerator is 3 root 3 plus pi, and the bottom is 3 minus pi root 3. Funky answer. I'll bet that is pretty close to -1 though. Okay? Funky answer there. Sorry, it's messy. I'll be a little neater on the next example here. But it's a formula, right? Let's try the next one. Can I move it? Okay. Oh, I got a little more room on this one. Nice. Okay. So dy dx is dd theta of sine 2 theta sine theta over dd theta sine 2 theta cos theta. This is a formula. You're supposed to memorize it. Okay? The thing in parentheses is the function they gave us. Okay, so now we're going to do the product rule and the little chain rule too for this one. So the top is the derivative of sine 2 theta. So 2 cos 2 theta. 2 cos 2 theta times sine theta plus, and then sine 2 theta times the derivative of sine theta. Then the denominator starts out kind of the same way. It's 2 cos 2 theta cos theta plus sine 2 theta times negative sine theta. And I worked all of this one out and I got rad 3 over 5. This is a little bit more interesting graphically. It's a rose. It looks like this. And we just found the slope right here.
So is the polar FRQ due Friday then?
The polar FRQ I'm going to hand to you now on your way out. And I'm going to make it due Friday. You can't do all of it. See, you don't know how to find area yet, but you can do like number 4, B, and C, and maybe parts of the second one I gave you.
This is it, right?
Yes, it's right here next to my projector. Grab a copy. So tonight you'll do just